we can derive properties of the graph of y equals f inverse from properties of the graph of y equals f of x, since they are reflections of each other in the line y equals x. And here's a couple of examples. If f is a one-to-one function, then of course it passes both the horizontal line test as a function and the vertical line test as a one-to-one function. And since horizontal lines become vertical lines when reflected in the line y equals x and vice versa, the graph of the inverse function also passes both of these tests and has to be a one-to-one function. So therefore the inverse function also has an inverse. And since the graph of f is the mirror image of the graph of f inverse in the line y equals x, f must coincide with the inverse function of f inverse. So f is the inverse of f inverse. If f is continuous, then f inverse is also a continuous function. Although it doesn't constitute rigorous proof, it's intuitively obvious that if I draw the graph of f, or if I can draw the graph of f without lifting the pen from the paper, then I can draw the graph of its mirror image, f inverse, without lifting the pen from the paper also. So f inverse must also be continuous. The derivative of f inverse is also related to the derivative of f. The exact relationship is shown in the formula here below. If f is one-to-one and differentiable with an inverse function f inverse, and suppose that f prime, or the derivative of f, applied to f inverse at some point a is non-zero, then the inverse function is differentiable at a, and f inverse prime of a is 1 over f prime applied to f inverse of a. Now this formula looks complicated. It's probably easier to see what it's saying with these outside descriptions of what these things are. We're saying the derivative of f inverse with respect to x, evaluated at some point a, is the reciprocal of the derivative of f with respect to x at x equals f inverse of a. We can see this in two ways. Both are equally important. One is using algebra, and again we're going to use this to derive the derivatives of functions like arc cosine later. Recall that y equals f inverse of x is the same as saying that x equals f of y. Using implicit differentiation, I can differentiate this equation with respect to x. The derivative of the left-hand side with respect to x is 1, and for the right-hand side, I have to use the chain rule. The derivative is the derivative of f with respect to y times the derivative of y with respect to x. And now I can rearrange that equation by dividing across by f prime to get 1 over f prime of x is dy dx. But what is y here? Well, y is actually f inverse of x. So the right-hand side of this equation, dy dx, becomes f inverse prime of x. And I'd like to find a formula for that, and I see that it's 1 over f prime of y. But once again, y is f inverse of x, so I can replace y by f inverse of x in this formula. And that's exactly the formula we have here. F inverse prime of x, or the derivative of f inverse with respect to x, is 1 over the derivative of f with respect to x, evaluated at f inverse of x. Now notice I can apply this formula without having a formula for f inverse, especially if I can find f inverse of a point A without solving for a formula for f inverse. There's a geometric way of seeing this, which depends only on pre-calculus knowledge. We know that the slope of the tangent to the graph of f and f inverse, these must be mirror images of each other. For any given line with slope m, its reflection in the line y equals x will have a reciprocal slope. It's going to be 1 over m. Recall also that if f inverse of a is a point on the curve y equals f inverse of x, then its reflection on the line y equals x, f inverse of a is on the curve y equals f of x. So the slope of the tangent to the curve y equals f inverse of x at a point a, f inverse of a, is going to be f inverse prime of a. And the slope of the tangent line to the curve y equals f of x at the point which is the mirror image is going to be f prime f inverse of a. But of course those two tangents at those 2 points are also going to be mirror images of each other. Their slopes are going to be related in this way. F inverse prime of a is going to be 1 over f prime of f inverse of a. Let's look at our 2 familiar graphs. The graph of f of x equals 2x plus 1 over x minus 3 shown in blue, and its inverse shown in purple here. And recall before we said the point 10, 3 was on the graph y equals f of x, and therefore its reflected image 310 is on the purple graph, the graph of y equals f inverse of x. If I want to calculate f inverse prime of 3, it's going to be the slope of this tangent here to the graph y equals f inverse at the point 310. And what we're saying is that the slope of that tangent is 1 over the slope of its mirror image in the line y equals x, which is the tangent to the graph y equals f of x at the point which is the mirror image of 310 at the point 10, 3. You should check that f inverse prime of 3 is 1 over f prime of f inverse of 3, which is f prime of 10, by calculating the derivative of f from the formula and the derivative of f inverse from the formula. And you'll see f inverse of prime of 3 is minus 7, but the slope of the tangent here at f prime of 10 is equal to negative 1 over 7. So it's the reciprocal. How can we use this formula? Well, we're going to use it in 2 important ways. The first way is going to be to find a formula for the derivative of some of these new functions we're going to look at, which we're just going to define as inverses of one-to-one function, such as the arc cosine function, which by definition is the inverse of the restricted sine function. And the other way we're going to use this is to solve for f inverse of a, in particular at a point where we can't necessarily find a formula for f inverse. So we're going to use what we did before in solving for f inverse of a without actually finding a formula for f inverse. Let's look at what's involved in one briefly. Arc cosine is the inverse of the restricted cosine function we saw, and what this formula is saying is that the derivative of this inverse function, arc cosine of x with respect to x, evaluated at any point x, is going to be 1 over the derivative of the restricted sine function at f inverse of x, so at arc cosine of x. Now remember, the restricted cosine function looks exactly the same as the cosine function on its domain, so its derivative is minus sine wherever it's defined. We're going to return to this problem in more detail in later lectures. In particular, we can use trig identities to find a formula in terms of x for sine arc cosine of x. In the next video, we're going to look at lots of examples of applications of type 2.